Let's take a look at the last problem from the Invader lecture that we didn't get to. It's got an A and a B, so make sure you have it in front of you as I reference the different parts of this question. So, starting off with part A, you'll notice that it cross-cuts a couple different ideas here because it's giving us grams of the sodium hydroxide and wanting to calculate pH. So grams is definitely no good because I need a molarity for pH. So right away, I can take the 4 grams of sodium hydroxide and let's go ahead and turn that into moles. All right, so I'm going to make the diagonal match. And we're going to go from grams to moles. And I know that when moles is over grams, it's 1 over periodic table. So we would need to go to the periodic table and add up Na plus O plus H. And you're going to get 40 if you add up the molar masses. All right. So as we solve this, we're going to find out that we've got 0.1 mole here, all right? And this number is actually going to be important for part B that we'll work on in a moment, the fact that 4 grams is 0.1 moles. But so we'll reference that again in a moment. But anyhow, now another given value is 0.5 liters, all right? So in the problem, it tells me that there is 0.5 liters of the solution. So if we go ahead and solve for molarity, moles divided by liters, of course, we're going to get 0.2 molar. All right. Now, the sodium hydroxide here is strong. Therefore, I don't have to do any extra thinking here because for strong samples, I can just take the negative log of the molarity. All right, and in this case, it's going to give me a POH because I'm taking the negative log of a base. So I'm going to get a value here of 0.7. The problem wants pH, which I know these added together will equal 14. Therefore, the pH must be 13.3. So that's part A of that problem. So let's go ahead and move to part B. That'll be a little bit more application of invaders. All right. So part B, again, you'll notice it says suppose that 4 grams of sodium hydroxide, which is what it started part A with, which is why the earlier calculation will be helpful. But it says that it's going to be added to a solution containing NH3 and NH4+. Now, by definition, this is a buffered system because I've got a weak base and a conjugate acid here. So if I'm going to add sodium hydroxide to it, which is a strong base, we're going to represent that base with just the OH because that's the defining characteristic. And of course, the negative wants to interact with the positive, so that's who he'll interact with when dumped into the buffer. The first step of invasion is always a normal arrow because we're analyzing a strong addition. So we can go Bronsted-Lowry here where this base wants to accept an H, which is going to form water, and the leftover right here will be ammonium, or ammonia, sorry. All right. And now remember, we have an invasion here, so I first want to find moles and compare them together to see who's going to be used up. I found in the previous problem that the moles of my NaOH is 0.1, so we can just add that right here. All right. And then to find the moles of the NH4, we'll have to go back to the problem, and we can see that we've got the NH4 is 0.5 molar at 1 liter. And remember, liters times molarity equals moles. All right, so it's really just times 1, so that's going to come out to 0.5. All right, and there won't be, water's not going to affect pH. We don't have any of this initially, or do we? Dun, dun, dun. All right, so here's where this problem's a little bit different, and that's why it made it into the lecture, or was supposed to anyway. But you'll notice that we do have an initial concentration here of the NH3. All right, the initial concentration of the NH3 is sitting there at 0.5. Again, times 1 is going to be 0.5. For the mole. So there, you just got to read the problem carefully, and you can easily trace that. All right, so anyhow, the smaller number here is the 0.1. That's what's going to be used up first, so that's what we're going to subtract, and we'll see that the strong base loses. All right, and then we're going to have some leftovers here of, it looks like, 0.4. And we want to shift up over here, which is going to make it end up as 0.6. All right, so remember, these are moles that we have. Now, in the previous problems, I've showed you that we should now divide the moles by liters to get back to molarity, and that's a fine habit to be in. However, if you're going to use the Henderson-Hasselbalch equation, you don't have to do that just because the ratio is the same. So anyhow, you're fine too. You could divide the 0.4 and the 0.6 by what would have been just 1 liter. Oh, in this case, it is just 1 also. But anyhow, for future problems that use the Henderson equation, you can actually skip that one little part. But I know some of y'all get nervous when it makes them different. Anyhow, the problem gives you a KB of 1.8 E negative 5. So that's a given value that's important. And now we're able to move forward with Henderson-Hasselbalch. Now we're using KB, so the equation is going to naturally give us POH. And following your equation, you'll see that it's negative log of KB plus the log of the ion over the sample. So if you look here, you'll notice that the ion, the conjugate, is 0.4, while the weak sample, the non-ion, is 0.6. All right, so run that equation in your calculator. I don't know where mine is. Where's my calculator? Okay, so if we plug this in as it appears, it would be negative log of 1.8 E negative 5 plus the log of 0.4 over 0.6, and it spits out a POH of 4.57. All right, now if you go back to the question, though, it wants to know, calculate the concentration of hydroxide ion. It wants to know what is the concentration of hydroxide ion. So it's actually good that we have a POH since these two things connect to each other, because in order to go from a POH to an OH concentration, we just take 10 to the negative POH. All right, so we can go 10 to the negative 4.57, and I get 2.7 E negative 5.